this is section 3.5. This is the complex zeros and the fundamental theorem of algebra. So we're going to be looking at and finishing off polynomial or look at polynomials, and this is going to be finding the zeros of every polynomial, finding all the zeros, not just the real ones as in 3.4, but all the zeros, including complex zeros. And we're going to look at the fundamental theorem of algebra and what that means, and how we're going to use that, and the linear factorization theorem to write factors in completed form. So we learned that x-intercepts of a polynomial are real zeros, but what about this polynomial, x squared plus 1? What about that one? Well, if we graph it, let's take a look at what's going on. If I graph x squared plus 1, which is just the x squared shifted up 1 unit, you can see that it does not cross the x-axis. Okay, there are no x-intercepts here. So the question then is, does this mean there are no zeros? And the answer to that is no, there are zeros. Okay, we understand complex numbers now. If I solve this equation, I can get x is equal to plus or minus the square root of a negative 1, or which means it's just plus or minus I, the complex number. So those become the zeros because a solution to the equation are the zeros. These are just not real solutions. They are complex solutions, which means you're not going to get the x-intercept part. This is why when I showed you those function comparison stuff where a zero is an x-intercept, provided that the zero is real. When I have complex zeros, the graph will not cross the x-axis for those zeros. And so we're going to use that to our advantage when finding all these other zeros. Some things we need to watch out for. Only the real zeros lead to x-intercepts on a graph. Complex zeros are turns or bends in the graph away from the x-axis. So it bends. This is a turn. You can have a bend. Complex zeros are typically found using solving squares technique, okay, which I just showed you, where you don't have a middle term. You can just solve for this right here, or using the quadratic formula, as we did with the irrational zeros. Because of this, irrational and complex zeros come in pairs. From the quadratic formula, you're going to get to, or solving the squares thing, you're going to get this plus or minus, meaning you're always going to get two solutions. They come in pairs. They're called conjugates. For irrational zeros, it's of this format right here, a plus the square root of b, a minus the square root of b, and for complex, a plus bi, a minus bi. So if you have one of these, then you have both of these, because you can't have just one. They come in pairs. So we want to keep that in mind as we do this. The fundamental theorem of algebra basically says this: the polynomial of degree n has n complex zeros, real and non-real. Remember, all the real numbers are also complex. So if I have a polynomial of degree 5, I'm going to have 5 zeros. They could all be real, or they could be a mixture between real and complex. Some of the zeros may be repeated. So if I have, we talked about multiplicity already, so if I have a zero that happens 3 times, then that counts for 3 of these zeros. The linear factorization theorem says that you can factor all polynomials into a product of n linear factors, n being the degree. So if I have a degree 5 polynomial, then I can write the function out as a product of 5 linear factors. And remember, linear factors means x minus k, x minus the 0. That's a linear factor that they're referring to. And here's how it lays out. This a right here is the leading coefficient. Z1, Z2, all the way up to Z sub n are all complex zeros of the polynomial. So this is what we're going to be writing our answers in linear factorization form. So the leading coefficient, and then x minus each individual zero. So this is what I'll be asking you to do. So that is the extension. Otherwise, we're going to do exactly the same process we learned in 3.4, where we are going to graph the polynomial on the calculator, do the PRZ, possible rational zeros, and then use those in the graph to help whittle it down using synthetic division to find all the zeros. If I get to a point where I can't find any more zeros, then I'm going to use the quadratic formula to find any irrational zeros if it crosses the x-axis at 2 points I can't find, or complex zeros if it doesn't cross the x-axis anymore. So let's do some examples all the way through and see how this is done. I'm going to not do the graphing on paper, but we will do it on the calculator. So here's our first example. We're going to do f of x is x to the fourth minus 8x squared minus 8x plus 15. So I want to find all the zeros for this function and factor it in linear factorization form. In other words, factor it completely. Normally what you would do on the test situation is you're going to graph this. So our graphing here is going to be just on the calculator. You would also, to graph this, go to section 3.3 video on graphing to show how to graph something properly. So we're going to graph it on the calculator, and I have already done so. And we see this graph right here. So you can see that I have two x-intercepts, and this little turn right up in here does not cross the x-axis. I have a degree 4 polynomial. So by the fundamental theorem of algebra, I know I'm going to have 4 zeros, but only 2 of them are going to be real. And so when you see something like this, this is indicating that you're going to have complex zeros. So based off of this right here, we can go through and we're going to see if we can figure out what all these zeros are. So there's my graph. Before I go to the graph again, I want to find the possible rational zeros. Factors of 15, factors of 1, all the top divided by the bottom numbers. So that means I'm just going to have plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. So if I have a rational zero, it will be one of these. So now we go to our graph again, and we look at the x-intercepts, and we ask the question, does it look like it goes through one of those numbers? Well, the scale is going out to 10, so I don't think 15 is going to be involved. In fact, I can look at it right here. It might be hard for you to see, but it looks like I have a 0 at 1 and a 0 at 3. So keep that in mind, 1 and 3, which are both in my list here. So then I'm going to confirm those by doing synthetic division. So the first one was 1. Let's do synthetic division with 1. You need to put all the coefficients into the top, remembering to put a 0 for any missing terms. You will notice that there is no x to the third term up here. So there's the x to the fourth, that's x to the third, x squared, x, and then the constant. And under the constant, I'm going to put a little box, and hopefully, if everything goes well, the remainder there will be 0. Bring down the first number, and then multiply. Add, multiply, add, multiply, add, multiply, and sure enough, 1 has been confirmed. The next one we said looked like it was going to be 3. So I'm going to confirm that 3 is indeed a 0 also. Just continuing this process helps keep factoring this problem out. Each time we do one of these zeros, we're also factoring out a factor of x minus these numbers. Bring down the first number, and you multiply. Then you add. Then you multiply. Add. Multiply. And sure enough, that one works. Now, based off the graph, we know that there is no more real zeros, so I can't do this anymore. So I'm going to write this out in what I currently have in factored form for the function f. The first 0 is x minus 1, because it's always x minus the 0, and then x minus 3, And then these numbers right here are the coefficients of the remaining factor. X squared plus 4x 5. The solutions to this equation can then be considered the zeros of this function. So that's what we're going to do. Sorry, I had a notification. Let's continue. So, quadratic formula, x equals a negative b plus or minus the square root b squared minus 4ac all over 2a. A is 1, c is 5, b is 4. Working this out, negative 4. And then this is 16 minus 20. So you can see that I'm going to get a negative 4 in here. The square root of a negative 4. And if you remember back when we did this, the negative comes out as I. The square root of 4 is 2. So now I have a negative 4 plus or minus 2i. And then I need to reduce this out. So negative 4 divided by 2, and then 2 divided by 2. So there's my two zeros right there. So I can list my zeros. And they are 1, 3, and you can list these together, 2 plus or minus I. So one is negative 2 plus I, the other one is negative 2 minus I. So you can list it that way. You can also separate them if you wish. That is the zeros list. The linear factorization goes like so. The leading coefficient is 1, so there's a 1 out in front, but we don't write it. And then it's the factor of each zero, x minus each of these zeros. So x minus 1, x minus 3, x minus, and then we put a little parenthesis here, negative 2 plus I, and then x minus a negative 2 minus I. And you can write it just like that for me. You don't need to simplify beyond that point right there. And so this is what we're going to be asked to do in the last section, or one of the things. So you just keep following this process. Quadratic formula gives me complex zeros, which come in pairs, or irrational zeros, which come in pairs. And you write the complex zeros and irrational zeros exactly the same way right here. Another item that you're going to be asked to do is the reverse of this stuff, which is literally this. What if I give you the zeros of a polynomial and you give me the original function? And so let's look at that concept right now. So here's an example. And usually what they will do is they will tell you certain things about, because the leading coefficient is important. So if I just give you negative 5, negative 1, and 2, they usually tell you, write an equation of a polynomial of least degree with a leading coefficient of 1. Meaning, the least degree means there are 3 zeros here, so the least degree would be 3. So that means you're going to do an x to the third graph. Leading coefficient of 1 means that this A out front, sorry, the A out in front will be a 1. Okay? So that's what you're going to do for this one, which means I have a function, the leading coefficient is 1, and by the linear factorization theorem, these are the zeros, then I have x minus a negative 5, x minus a negative 1, and x minus 2. And then your job is to multiply this out. Usually I just multiply the back two first, and we get x squared minus 2x plus 1 is minus x minus 2. And then distribute the next one here is x to the third minus x squared minus 2x minus 5x, and then minus 10. and you clean this all up. G of x is x to the third plus 4x squared minus 7x minus 10. And so that's one of the questions you'll be asked to do also. I'll give you the zeros. Usually it will say in the sense that they will say you have a leading coefficient of 1. And if they don't do that, then you need to find the leading coefficient. And I don't have an example of that one right now. We'll have to do that one in class. But here's another one where they have hidden zeros listed. So whether you do, let me do this one. So here's the zeros. I'm going to do 5, 5, and then 4 plus I. I'll do one with complex. So write a polynomial of least degree and a leading coefficient of 1. You have to ask the question, well, how many zeros are there? Least degree, I got to know the degree that I'm shooting for. Well, I have a repeated 5, so that's 2. This is 3, but this is complex. And so there's one that's not listed. Complex zeros come in pairs. You can't have just one. So there is another one that they did not list that you need to be aware of, and that's the conjugate of it. So when you write your polynomial, you'll write x minus 5, x minus 5, x minus 4 plus I, and x minus 4 minus I. So you have to write it that way. If you're going to multiply this out, you have 4 of them. A lot of times, this is a pair right here. Always multiply the complex or the irrationals together first. Because I have this, I can do these also. This is a special case right here. So this is going to be x minus 10, x squared minus 10x plus 25. And then this one over here, you might want to take a moment and distribute the inner negative sign just to make sure you don't have any sign errors. Don't try and do it in your head. And then multiply that out. Don't multiply an irrational or complex to a non-one. Always multiply it to its partner first, so that because if you do it right, you'll know because there will be no i's in this problem. All the i's will disappear. If you have i's when you get done multiplying, you've done something wrong. Same thing with the irrational. Because it has a square root in it. If you multiply correctly, there'll be no square roots when you're done. Take your time. X squared minus 4x plus ix minus 4x plus 16 minus 4I minus ix plus 4I minus I squared. X squared and x, 25. All right, what do you notice? See, the ix will drop out. The 4I will drop out. And I squared, remember, I squared is a negative 1. So I have minus a negative 1 or plus 1 right there. So x squared minus 8x, 16 plus 1, 17. Now I just got to multiply this out. And yeah, it's kind of long, but you're going to do it. Take your time. This is a test question. Minus 10x to the third plus 80x minus 170x 25x squared and then 200x and then 25 times 17 is, I have no idea. 425. And so you just clean up like terms. So f of x equals x to the fourth. Make sure it's in proper order. I got negative 8, negative 10. That's negative 18. I got 17 and 25, 42. The x's now, there's 3 of them. So we have this one, and that one. So if you take 80 from here, it gives me a negative 90. negative 290x, and then plus 425. So there you go. You'll be asked to do something like this on your next test. So graph it on the calculator, do your PRZ, compare the graph with the PRZ to find some possible rational zeros, integers. Okay, do the integers first. Do synthetic division to confirm that they are indeed zeros. Get it down as far as you can. You'll know from the graph and the number of zeros if you're going to have complex zeros or not. And take the one that's going to produce complex zeros, solve it using quadratic formula to find the two zeros. List all your zeros, write it in factored form completely. If I give you the zeros, then I want you to write the function. Make sure you know the leading coefficient. And then each zero is always x minus the zero. Be careful with your complex and irrational zero writing. Take your time when you multiply it out. You don't want to make a sign error. You don't want to make an addition error. And you get your final answer here at the bottom end. So this is what we're going to do today in 3.5. This is what you're going to be doing on your test. And this covers all of polynomials.